In this video, we're going to talk about limiting reagents. We did a lab in class where we were looking at making s'mores, and the equation for it, or the recipe for it, is to make one s'more using 2 wafers, 10 chocolate chips, and 1 marshmallow. So this becomes a balanced chemical equation. And then one of the questions in the lab asks you, what if you have 1534 marshmallows, 678 chocolate chips, and 271 wafers? How many s'mores can you make? So what a lot of you did was you took a look at each reactant separately. So something like this. Right? You said if you have 1,534 marshmallows, that will allow you to make 1,534 s'mores. And that's because 1 marshmallow makes 1 s'more. So the ratio you multiply by is 1/1. Then you took a look at chocolate chips. And because you need 10 chocolate chips to make 1 s'more. If you have 678 chocolate chips, you can only make 67 s'mores. So you probably divided by 10 to do this, but dividing by 10 is the same as multiplying by 1/10. And the reason we did this is because in Stoic, in the last video, we always multiply by the mole ratio, where the numerator is the number that we're calculating for, so in this case 1, and the denominator comes from the quantity that you were given, in this case 10. And these numbers, all these numbers come from the coefficients of the balanced chemical equation. Lastly, you were looking at wafers. So 2 wafers make 1 s'more, which means you have to divide by 2, multiply by 1/2, and that makes 135 s'mores. But at the end, what do you do with all these numbers? We didn't add them. By common sense, you know that if one of these ingredients, chocolate chips, only allow you to make 67 s'mores, well then that's all you can make. So it really doesn't matter that you can make 1,534 with 1,534 marshmallows. You didn't have enough chocolate chips to make anything more than 67. So now these two numbers become irrelevant. So again, by the same logic, it doesn't matter that you can make 135 s'mores with 271 wafers. The chocolate is limiting you from making more s'mores. So in chemistry, the reactant that is limiting us from making more reactants is called the limiting reagent. So in this case, our chocolate chip is our limiting reagent. And the other two is called excess reagent. So you don't always have to have 2 excess reagents. In a chemical reaction where you only have 2 reactants, one of them will be limiting, the other will be excess. Why is it called excess? Well, if you look at, let's say for example, marshmallows. We know that at the end we can only make 67 s'mores. So that means if you make 67 s'mores, you're only going to use 67 marshmallows, even though you have 1,534 marshmallows. So at the end of the reaction, you're going to have leftover marshmallows. And leftover in chemistry we call excess. So limiting reagent makes the least product. And it always gets used up first. So just like here, all 678 chocolate chips will be used up before wafers and marshmallow. In fact, you will have leftover of this reactant. You will have leftover wafers and you will have leftover marshmallow. So the excess reactant is the one you have left over of, and you have too much of. Which actually is the same thing. So now let's relate this to a chemical reaction. Okay, chloride dioxide, ClO2, is a reactive oxidizing agent. It is used to purify water. They gave you the balanced chemical equation. So 6ClO2 plus 3H2O reacts to produce 5HClO3 plus HCl. Question 8 asks, if 71.00 grams of ClO2 is mixed with 19 grams of water, what is the limiting reactant? And then B says what mass of HClO3 is expected in part A. So I like to spread my equation out so that I can do math on it. So I'm going to write it out again. 6ClO2 plus 3H2O reacts to produce 5HClO3 plus HCl. And they are giving us 71.00 grams of this and 19 grams of water. And I'm going to set up my chart again. So my chart always goes mass, molar mass, and moles. So they only gave us mass. Can you use mole ratio with mass? You can't. So why can't you use mole ratio with mass? The analogy, the comparison here is when we're using these mole ratios here, these fractions here, we were looking at quantities. Right? We have an exact number of marshmallow, an exact number of chocolate chips, an exact number of wafers. Well, what if they give you mass? And what if they say, well, I have 100 grams of marshmallow and 500 grams of chocolate chips and, I don't know, 700 grams of wafers. Well, giving you mass isn't helpful because even if they tell you they have 500 grams of chocolate chips, you have to figure out exactly the number of chocolate chips so that you can say, well, I'm going to make this number of s'mores. So having mass isn't useful unless you can figure out how much quantity is in the mass. So like 100 grams, how many marshmallow is that exactly? So just like here, having quantities isn't really useful unless we change it to moles. So we're going to change each one to moles. So in this chart, we're going to go from mass to moles by dividing by the molar mass. So mass, each of these mass divided by the molar mass is going to give us moles. So that would give us 1.056 moles of water and the molar mass of ClO2 is 67.546 grams per mole. And 71 divided by 67.546 would also give us 1.051 moles of ClO2. So again, I'm doing this as if it's in the column. So this column right here is for water, this column right here is for ClO2. So now we know that we have this many moles of ClO2, this many moles of water. Well, question A asks you, what is the limiting reagent? So again, you have to figure out which one gets used up first, which one makes the least product. And in here, they didn't really tell you which product to calculate for. So technically, you can choose any one of this and say, well, water, this many moles of water makes this many moles of HCl. And then this many moles of ClO2 makes this many moles of HCl, and then choose the least one. But if you look at question B, it specifically asks you for HClO3. So if we calculate for HClO3 here, then we can save some steps in part B. So let's do that. So we'll calculate how much HClO3 this amount of water allows us to make, and how much HClO3 this amount of ClO2 allows us to make. So we're taking a look at each ingredient or each reactant and how much product each of them allows us to make. Just like how in this question we looked at each of these ingredients or each reactant and we took a look at how many product each of them allows us to make, and then we chose the least one. So we're going to do the same thing here. So the mole ratio you have to multiply by for water is 5/3, because you took the numerator from the quantity that you have to calculate for and the denominator from the quantity that's given. And the ratio here is 5/6. So this number would be 0.8759 moles of HClO3. And then this quantity here is 1.7592 moles of HClO3. Okay, so a reminder that we have moles of water and we had moles of HClO2, but once you do the mole ratio, once you multiply by the mole ratio, these numbers are not about water, nor are they about ClO2. These numbers are now about HClO3, okay, or chloric acid, right? So once you multiply by the mole ratio, the purpose of multiplying by a mole ratio is to figure out how many moles of HClO3, chloric acid, you will make. So this tells us that this amount of water will make 1.7592 moles, and this amount of chloride dioxide will allow us to make 0.8759 moles. So what do? We choose the least one. So this number is irrelevant. We can only make this many moles of HClO3. So we're saying that even though this amount of water allows you to make 1.7592, well, you don't have enough ClO2 to make that many. You only have enough ClO2 to make 0.8759 moles of HClO3. So now knowing that, now knowing how many moles were made, we can then, I'm going to write on a separate line, use the number of moles multiplied by the molar mass of HClO3 So that would be 84.546 grams per mole. And that is the mass of HClO3, or chloric acid, that you'll make. So that amount of moles is equal to 74.05 grams. And we are using 4 significant digits because the original question gave us 4 significant digits for both masses. So our answer for A is that ClO2, I'll write it here. For A is that ClO2 is a limiting reagent because it makes the least product, and for B, our answer is that 74.05 grams of chloric acid can be made. So those are our 2 answers. So also something else to look out for, right? One of the things is if you just look at the mass, so go back to the beginning, just look at the mass that's given. Having less mass doesn't mean that it's going to be a limiting reagent. So you cannot simply look at the mass of each reactant and say, oh, there is less mass for water, therefore it will be limiting. In this example, it's the opposite, right? You have less mass for water, you have a higher mass for chlorine dioxide. But when you finally calculate how many moles there are and use mole ratio to calculate how much product each of them can make, chloride dioxide is the limiting reagent. So mass is not an indicator of which one is the limiting reagent at all until you take into account the molar mass and the mole ratio. Because even though you have less mass here, well, each mole of water, first of all, has a less mass, and you don't need as much water in this reaction. So the masses here are irrelevant. You have to really take a look at how many moles you have, and then take a look at the mole ratio. Okay. Second of all, the second thing I want to point out is, if you look at the moles, even just comparing the moles here won't give you the limiting reactant, right? Because this is almost the same amount of moles, and yet even with the same amount of moles, equation tells you you need less water. You only need 3 water for every 6 chloride. So even chloride dioxide. So even if you have the same amount of moles, it doesn't mean that each of them will allow you to make the same amount of product. So in this case, you have very similar amount of moles, but one of you allows you to make way less product than the other one. So don't determine the limiting reagent by mass, and don't determine the limiting reagent by the moles of each reactant you have until you have multiplied by mole ratio. That shows you how much of the product each reactant allows you to make.